Oracle locks, latches, and waits. A while ago, I was sitting at work, and one of my coworkers just came by and said, "What are you doing? You're just sitting there. Why aren't you working?" And I said, "Well, Bob is updating a Word document that I need, and so I'm just waiting on him." So Bob had a lock on that document, and it was causing a wait event. Well, then I tried to browse the internet to find some information I needed to get some work done, and it took about 5 seconds for that page to render. So that too was a wait event. And then later on, I needed to call up another coworker and ask a question, and well, it took about 10 rings for him to pick up. That was another wait event. And then he told me, "Hold on a second, I'm in the middle of something. Let me get back to you in just a second." Yet another wait event. Then I decided to take a break, go to the restroom. Somebody was already in the stall. That was actually a lock on the restroom, which caused a wait event. So in everyday life, we encounter all sorts of locks, latches, and wait events, as we do with Oracle databases. It's important to understand what locks and latches are and how they differ, and also what these wait events mean, so we can tackle larger performance tuning problems. So in our next nugget, we'll talk about performance tuning. So the first thing we'll talk about is the difference between latches and locks, and the different lock modes. There's 6 different lock modes. And then we'll take a look at some data dictionary views to see what is locked up in your database. And then we'll take a closer look at some of the more common types of latches and locks. There's lots of different types, but these are the more common ones. For example, transaction locks and row-level locks. That has to do with when you're performing DML activity on data and you don't want another session to modify a data at the same time that you are. We've got buffer locks, that's used on the buffer cache. We've got data dictionary locks to prevent objects from mutating from under your eyes while you're modifying it or querying it. We've got NQ latches. There's a lot of different types of these NQs. We'll take a closer look at those. And we've got library cache locks and latches. Remember, the library cache is used to store your cached SQL statements. So we have locks on those components in memory. So after we talk about our locks and latches, then we'll talk about the Oracle Wait Interface. That's what OWI stands for. The Oracle Wait Interface is simply a collection of data dictionary views that gives us insight as to what's really going on in our system as far as waits are concerned. Oracle server processes sometimes need to wait on things. For example, maybe a resource isn't available, or maybe there isn't any work to do for a server process quite yet. Maybe it's just sitting idle, or maybe it's waiting for another server process to perform a task. So we can use this wait interface to look at wait events on the system level, on the session level, and then we have another view called $session wait, which gives us real-time information on the wait events. And then we have $event name, which is just a lookup view to tell us what the different event names are. We'll inspect some types of waits. For example, DB file sequential read waits have to do with index lookups. DB file scattered read has to do usually with full table scans. We've got direct path read and write events, as well as NQ, buffer busy wait, library cache pin. Once again, these are some of the more common types of waits. There's a whole lot more out there. So let's first of all talk about our latches versus locks. There's numerous data structures in the SGA that need to be accessed concurrently. For example, we've got the buffer cache, we've got the library cache. Latches and locks are there to ensure that only one process is modifying one of those structures at a time. Okay, so the big difference between latches and locks is that latches allow only exclusive access to the data structure. So if 2 processes want access to a latch on a data structure, one will gain access and the other is going to spin for a short period of time and either time out or then gain access after the other one is done. Whereas locks are going to allow concurrent access by a process, but only one can write at a time. Usually a latch on an object is going to be for a really short period of time, whereas locks can be a longer period of time. For example, if I have a lock on some rows in a table, I might have that exclusive lock for over an hour, whereas with latches, it's usually going to be under a second. A while back, I was helping a team author a book, and we decided to divide up the different chapters between us all. And what I needed to do was look at one of the chapters that somebody else was writing. And I said, look, I don't need to make any modifications. I just want to view it to see what, how the progress is going. And so that would be an example of a lock. Now, if you had somebody working on the chapter and saying, look, I'm real protective about my information here, and I don't even want you to view what's going on here while I'm writing, then that would be an example of a latch. You can really run into some performance issues if you've got a lot of processes trying to access the same data structure that is held under a latch. And you could also encounter some really serious performance issues if you've got two processes trying to access the same rows in exclusive lock mode. Let's talk about our different lock modes. Before we talk about the different lock modes, let's talk about various types of objects. We've got simple objects and we have compound objects. An example of a simple object might be the buffer cache. It doesn't have any sub-objects. An example of a compound object might be a table. Well, its sub-objects would be the rows within the table. For simple objects, there's only 3 modes that a lock can be held in. The first mode is exclusive mode. So if a session needs to modify that type of object, that would be in exclusive lock mode. Then we've got shared mode. You can have a shared lock on an object, and there can actually be multiple shared locks by different processes on the same object. And what that shared lock does is it prevents other processes from making modifications to it. The only time a process can place an exclusive lock on an object is when there are no other locks on it. We also have what we call a null lock. This is kind of like a placeholder. So if a session caches information about an object, then a null lock is going to be placed on that object, and it's going to kind of like act as a trigger in case the object is invalidated. An example might be if you query a table and those database blocks go into the buffer cache, and then the table structure changes. Well, that object has been invalidated. The next 3 types of locks are used only for compound objects. For example, we have sub-shared lock. This is where we need to have a shared lock on a sub-object. For example, if we want to place a shared lock on some rows in a table. If you create a cursor and use the forUpdate clause, this is going to place a shared lock on the affected rows of this cursor. Then we have a sub-exclusive lock. This is used if a session needs an exclusive lock on part of a sub-object. For example, if we said update employee, set salary equals salary times 1.1 where department equals 10, it's going to place an exclusive lock only on the rows where the department number equals 10. And then we have a hybrid of these 2 types of locks. This is called a shared sub-exclusive lock. This is where a session needs exclusive lock on some rows in a table and a shared lock on a whole table somewhere. For example, if you had an update statement on a table and you're just updating some of the rows, but you're also using that in combination with a select statement on another table or on the same table. Now that you understand the different lock modes, we can look into our data dictionary views and find out information about our locks. Here are some really helpful data dictionary views that are going to let you look into what exactly is getting locked up. For example, DBA locks is going to give you information about the session ID of who's holding the lock, as well as what type of lock, what mode the lock is in, and whether or not it's blocking other sessions from access. This DBA locks view is going to describe all the locks on the system. Now, if you want to narrow down your locks to just DML locks, remember DML stands for Data Manipulation Language. So in other words, if you have sessions that are issuing inserts, updates, or deletes, well, you can query this view just to look at those. Now DDL, remember that stands for Data Dictionary Language. So if you're creating tables, altering tables, dropping objects, anything like that, anytime you're altering the structure of anything in your database, a DDL lock is going to be performed. Now these are usually pretty short-lived, so to actually peek into this real time is going to be somewhat difficult. And then we have a view called DBA blockers, which just shows which sessions are blocking other sessions for resources. And then we have DBA waiters, which goes the opposite direction. It shows us which sessions are waiting for resources, and it gives us more detailed information than DBA blockers. So we can use this in a join select statement to see which session is blocking other sessions. I'll show you an example of a DML lock in action. So I've got one window opened up for SIS, and I have another window opened up for Scott. These are tapping into the same database. Okay, so what I'm going to do is do a quick little describe on Scott's emp table, and by performing DML activity, either an insert, update, or delete, it's going to place an exclusive lock on the affected rows. So we can say update emp set sal equals sal times 0.9. We're giving some people a demotion, where department number equals 20. So 5 rows have been updated. I have not performed a commit or a rollback yet, so that exclusive lock on those 5 rows is still there. In our sys window, we can do a describe on DBA DML locks. And let's grab the session ID of who has the lock, as well as the owner, the name, the mode held from DBA DML locks. Now what's interesting is even though 5 rows are locked up in exclusive mode, there's only one entry in this view here. Where is all the detailed information about the locks held? Well, it's actually held at the database block level, inside of the block header. This mode held, row X, means row exclusive lock. We could have obtained this information by looking at DBA locks view as well. Now, let's see what happens when we perform a rollback on this transaction, and then we issue this statement again. There's no more DML locks for this transaction. Now let's look at how to use our DBA waiters view. I've got a session for Scott up here, and I've got yet another session for Scott right here. And what I'm going to do is have this session put a lock on some rows, and then I'm going to have this session down here attempt to obtain a lock as well. Once again, let's do an update statement. We'll say update emp set sal equals, let's give him a raise this time, where department number equals 10. Okay, now 3 rows were updated. I haven't rolled back or committed yet, so I still have an exclusive lock on those particular rows. Now let's go down here and try to perform an update statement. We can say update emp set sal equals, and let's just give everyone a demotion. And you see how we're locked up here? And the reason why is, well, we have those 3 rows that have the exclusive lock on them, and we cannot proceed further. So now we go into our other window for our sys. We can do a describe on DBA waiters. So you'll see that we've got a waiting session and a holding session. Let's grab that. Waiting session, holding session, and if you wanted to, you could do a join on the $V session table, or you can do it in 2 separate statements. We're going to grab the lock type and the mode held from DBA waiters. And you'll see that our waiting session is 140. The holding session, in other words, the session that has the lock, is 154. It is a transaction lock, and it is in exclusive mode. The only way we can get rid of this is by performing a commit or a rollback in the Scott window up here, or if you're logged in as a sysdba, you can kill that session off. I'm going to perform a rollback. And you'll see that as soon as I said rollback, down here I was able to update the 14 rows in our table. So at this point, this session down here has the exclusive lock on the 14 rows in the table. If you ever have end users calling you up saying, hey, my application is just hanging, then this would be one of the first places to look. Something to note about Oracle's locking mechanism is that there is no locking manager. Now, a lot of other relational database management systems have an object called a locking manager, and it can actually be a single point of contention. For example, if you've got a ton of transactions that are trying to lock data, well, you can have this one object keeping track of all the locking, and you'll just run out of resources. The way that Oracle handles locking is on the database block level. So what you're looking at here is a diagram of a database block. Now, I have data down here. The way data grows is we say it grows from the bottom up, and every single database block has a header. Now keep in mind that every row in your database block has a unique identifier called the row ID. And so Oracle keeps track of the row IDs up here in the header, and it also keeps track of transactions through what we call the interested transaction list. Every single database object in your system has storage parameters associated with it. We have inittrans, which represents the initial number of transactions allocated to a block, and it can grow up to whatever the max trans is set to. Now the default value for inittrans is 1 for tables and it's 2 for indexes. Max trans default value is usually 255. In other words, a database block has a minimal value of whatever inittrans is set to and a max value of max trans. So if we've got a session that's trying to get a lock on some rows, let's say one of the rows is in this database block, well, it's going to place that lock information in the header up here. Now, if there is another session that has a lock on it, then it's going to have to wait in the queue, just like you saw earlier. Remember how we had one session that was issuing an update on some data, and the other session had to wait until the first session either performed a commit or a rollback. There's also a couple other storage parameters. We have %free and %used. Let's talk about %free first. When we insert data into a block, it's going to keep growing up and up and up until it hits whatever the %free is set to. Well, let's say that this %free here is set to 15%. Well, why in the world would we want to waste space like that? I mean, why only grow the data up to this point and then leave this all empty? Well, imagine that you're inserting a bunch of records and then you decide, well, later on I might update these records. Perhaps there's quite a few null values in my columns. In later updates, I might replace those nulls with some actual data. So we're just allowing for updates up here. So the %used is kind of like the opposite of %free. %used just means that, let's say we perform a bunch of deletes in this block. Well, as soon as we hit below this %used line, then we're allowed to insert more records again. Well, if you think that you're not going to be performing that many updates, in fact, if you think you're only going to be performing inserts and deletes, then you probably want to have a low %free. The lowest I would go would be 5%. The reason why I would not go any lower than 5 is because you need to allocate some space for these transactions. If you set your %free too low, like the number 0, then you're going to probably get a lot of ITL contention. So it's best to keep it at a very minimum of 5%. Oh, and by the way, the default value for %free is actually 10, and the default value for %used is 40. So you can override these default values by setting the storage clause either on the table space level or the table level. If you want to see what the particular settings are for a table, you can just open up a window here and see how we're logged in as sys. You can do a describe on DBA tables. It's a pretty big table, and you'll see that there's a parameter or a column called inittrans and another one called maxtrans. And so we could say select inittrans and maxtrans from DBA tables. And let's say we were only interested in Scott's emp table. So we would say where table name equals emp and owner equals Scott. You'll see how they're set right here. There's other types of latches and locks besides the transaction locks and road level locks like we already talked about. For example, there's buffer locks. Every time a server process tries to get data from the database, it's going to first of all look in the buffer cache to see if that information is there, if the database blocks are there, and if not, it's going to pull the database blocks from the data files and into memory. So that's the buffer cache. If one process is either modifying one of those blocks or is reading it into memory at the same time that another process is, then there's going to be some contention there. So it might hold a buffer lock on particular database blocks. Then we have data dictionary locks. Remember, those are the DDL locks. For example, if I'm trying to access information in a particular table, well, a DDL lock is going to ensure that the structure of that table isn't changing. And then we have NQ. And NQ can mean a whole lot of different things. This is kind of a catch-all for a lot of different locks and latches. It just means that we've got a data structure and we're ensuring that two different processes can't modify that structure at the same time. For example, it might be holding a lock on a password file, or it might be holding a lock on a data file. So think of NQ as the catch-all. We also have library cache locks. A library cache lock occurs when one session executes a SQL statement. Well, that gets parsed, and that parsed SQL statement gets put into the library, into the shared library. Now, if another session tries to execute the same statement, well, that hash code of the SQL statement will already be in the library cache, and there might already be a lock on it. So we have all types of different locks. Now, what I want to show you are some of the Oracle wait interface components. For example, $$ system wait shows us wait events on the system level. We can look at session event for the session level. We can look at session waits, which gives us pretty much this information in $$ session event, except it's real time, and then a lookup table called $$ event name. But let's take a look at that. Okay, so we're logged in as sys. Let's do a quick describe on $$ system event. And you'll see that we have the event. And in 10G, they've added the wait class, so you can get the general type of wait that it is, whether it's I/O wait or network or application related. We have the total number of waits as well as the total number of timeouts. Remember, every wait event has its own timeout value. For example, X number of milliseconds until it will sleep. And then we can find the total time waited and how long the average wait lasted. And in 10G, we have something new, which is the time-weighted micro. We get the same value that's in microseconds. The time weighted up here is actually in 1/100ths of a second. Now keep in mind, all this wait information describes the wait events that have occurred since the database has been up. So if your database has been running for a year, these are going to be really large numbers. So don't panic when you see huge numbers for your wait events. In fact, a lot of your wait events are really normal. For example, we have what we call a PMON timer, which is the process monitor. So there's a timer. It's perfectly normal behavior. A lot of those wait events belong to the wait class called idle, which we just tend to ignore. I like to get the big picture of what my system is doing by saying select event. We'll get the total waits, average wait from $$ system event, where wait class does not equal idle. We don't care about the idle events. We'll have to format this to make this look better. Let's do a column event format A35 and then re-execute it. Okay, that looks better. It might make more sense to order these by the total waits or by the average wait. Let's do it by total waits. So we'll just, there's our buffer, and we can say order by 2. You'll see down here that we've got a DD file sequential read. That actually has to do with index lookups. So that's an I/O wait. And then the next two up have to do with control files, reading and writing to them. And then our log files. And then we've got DB file parallel write. That's if you've got more than one process trying to write to a database file. And then DB file scattered read usually has to do with full table scans. For example, if I say select star from emp, Oracle's going to scan the whole table, which isn't always a bad thing. If you've got a smaller table and you do a full table scan, it's not going to be a horrible thing. If you've got a table that's in the petabytes, then yes, it's a very bad thing. So keep in mind that this just gives us the big picture. Now, if you want to drill down, let's say a user calls you up and says, oh, I'm having horrible performance with an application. Well, you should ask them, okay, what's your username? And drill down into the $v session event. Let's do a describe on that. And we have a lot of the same fields. The only difference is that we have the SID. This view is going to describe wait events per session since the session has started up. So if the user calls you up and says, look, I started this application 2 hours ago and I'm getting horrible performance now, well then you can just do about the same query that we just did, find out which events are the culprits, and then we could drill down further into the $v session wait. You could find out from looking at your $v session what the SID is of the user that's having problems. And let's assume that we've drilled down to this $v session event and we found that the event is some kind of locking that's going on. Well, then drilling down into $v session wait is pretty easy. We could do something like this. Select event. The P1, P2, and P3 columns mean something different for every type of wait event. For example, for some events it pertains to a file number, a block number, and a row number, which is the case for transaction locks. We can also find out the seconds in wait. We can see the state, whether it's waiting or not. Okay, so let's look at the event and how long it's been waiting. So seconds in wait and the state from $v session wait where SID equals, and let's assume that we've already figured out that it was SID 142. Okay, so we've got some row lock contention. Oh, we've been waiting 601 seconds in that wait, and it's still waiting. We can actually find out a lot of this information by looking directly in our $v session view. And in fact, it's easier to find that information from here. So you'll see that we have a blocking session, blocking instance. We can find who the culprit is, or more importantly, we can find out what information it's trying to grab. For example, we can grab the object number, the block number, and the row number. Let's do that. We'll say select row wait object number, row wait block number, and even drill down into the row number. Let's also find out who the blocking session is, where SID equals 142. Okay, so our object number is here, the actual block number is right here, and this is the row number within the block. Now, if you want to find out what that actual object is, it's pretty easy. Let's do a describe on DBA objects. Okay, let's grab the owner and the object name from DBA objects, where object ID equals 51161. It's the ScotEmp table. Now at this point, this is where you decide what you want to do as a DBA. You could be really rude to the blocking session and just kill them off, or you could give them a warning phone call asking them to kindly either commit or roll back. I'm feeling pretty rude today. I think I'm going to go ahead and kill this session off. Now to kill off a session, you need to know not only the SID, but also the serial number. So we can say select serial number from $v session, where SID equals 142. Okay, so now the SID is 142, the serial number is 177. Now this is the culprit that we're trying to kill off. So we simply say alter system, kill session, and then in single quotes, 142 comma, 177. That's almost too easy. Let's assume that a user calls you up and asks you to take a look into the session events, and you do that, but all you're getting there is the session wait information since their session has begun. How about if you want to see things real time? Well, you could look at your $V session wait view. You could do a query on that view in rapid succession and get some very, very different results. If you want to capture everything that's been going on in a trace file for that session, then you can turn on tracing for that session. So you would instruct the user to do an alter session set events 10,046 trace name context forever level, and you can have several different levels. Level 8 just means that you're capturing the wait event information. Level 4 means you're grabbing bind variable information. Level 12 means you're grabbing both. We're only interested in the wait information. What we're doing here is looking deeply into Oracle internals. Okay, so the session has been altered. So from this point on until we turn off the tracing, we're capturing everything about the wait events. Then, when they want to turn off the tracing, they simply change this to say trace name context off. At this point, you would go into the user dump directory and look at their trace file to see exactly what's going on. By the way, the only way these OWI components are going to work is if you have a parameter called timed statistics set to true. And by default, it is already set to true. Just to double check, you can do a show parameter timed statistics. So if you find that it's false for some reason, maybe somebody modified it, just do an alter system set timed statistics equals true. When you're looking at the results of these $V system event or $V session event, it's important to understand what some of these mean. I'm going to show you how to read the symptoms of your database, but I'm not going to show you quite yet how to fix it. We'll do that in our next nugget on performance tuning. First of all, DB file sequential read, that usually has to do with indexes. Well, why does it use the keyword sequential? Well, it just means it's reading some database blocks into contiguous memory. So that's where the sequential comes from. And this is usually a result of reading a single block. I know it's a little counterintuitive, but DB file scattered read often has to do with full table scans. For example, if we say select star from emp, it's going to read every single block in the table. The reason for the scattered keyword is because when it's reading these database blocks, there's usually not contiguous memory for all these different blocks, so they're going to be scattered throughout the memory. Then we have direct path read and write. Remember back in our nugget when we talked about import and export utilities? And there was a parameter called direct where we could bypass the SGA altogether and have information go directly to write or read. Well, this type of wait event is related to that. This might also be indicative of a really heavy sort operation where we don't have enough memory to store all the data we're sorting. So when that happens, Oracle is just going to take part of the data that we want to sort and put the rest to disk in our temporary table space, and then later it's going to read from it or write to it directly. Then we have our enqueues. Remember, those have to do with locks and latches. There's all sorts of enqueues. We have some for data files, control files, log files, password files, memory structures. And then our buffer busy waits. This has to do with contention on the database blocks in the buffer cache. Usually the way to fix these buffer busy waits is to tune your SQL statements. And the library cache pin wait means that a session is preventing other sessions from modifying any parsed SQL. This usually is happening when Oracle is compiling or parsing out a SQL statement. There's ways to improve those metrics as well. In this nugget, we talked about latches versus locks. Remember, the difference between a latch and a lock is that a latch provides exclusive access to an object, and that includes read access. Whereas with a lock, you might only have one session modifying a structure and others can read. So typically the latches are going to have very short access to it, and a lock, well, a lock can last for quite a long time. And we have our different lock modes. Remember, shared just prevents exclusive access to an object, whereas exclusive mode means that you're the only entity that can write to this object. And then some of our data dictionary views that help us to peek into our locks that are going on. Remember, we had DBA blockers, DBA waiters, we had DBA locks. And then if you want to see the locks for DML and DDL activity, we have the DBA DML locks and DBA DDL locks. Then we talked about our different latches and locks and the associated wait events for those. For example, our transaction locks are highly related to our row level locks. Whenever you're trying to insert, update, or delete records into a table, well, that's going to perform an exclusive row level lock, which is managed by the transaction lock. And once again, we don't have a locking manager in Oracle. It's all done on the database block level by using the database block headers. And we have those interested transaction list slots in the headers of our database blocks. We have our buffer locks for the database buffer cache, our data dictionary locks for performing DDL activity. We have all sorts of enqueues, as well as the library cache used for parsed SQL statements. I gave you the tools for peeking into the wait activity on your database. We can look at the system as a whole by looking at $system event, and this is activity since the database has been up. And then our $session event, activity since a session has started. And then real-time information, $session wait. And then we looked at some different types of wait indicators. For example, DB file sequential read, usually having to do with index lookups. DB file scattered read, usually when you're performing full table scans. We have direct path read and write, occurring usually when we're doing direct path activities such as the import, export, or if you have a sort that's overflowing. We have our enqueue waits, the buffer busy waits, which are highly related to the buffer locks up here, and then our library cache pin waits, having to do with parsing and compiling SQL statements. Well, I hope this has been informative for you, and I'd like to thank you for viewing.